Hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this particular discussion, we're going to look at a way of representing Gibbs-Helmholtz relationship in terms of a partition function. And this, of course, is going to be achieved through the use of the Gibbs-Helmholtz free energy. Now, in our previous discussion, I mentioned that there are various, of course, applications in this aspect of the Gibbs and Helmholtz free energy, whereby we say that they are going to represent the aspect of spontaneity of chemical reactions. And of course, from this one, they are going to create the relationship between different states of equilibrium. And of course, we have said that from the Gibbs-Helmholtz energy, we can be able to evaluate the concept of, or rather calculate the enthalpy of various reactions by having a knowledge of either the Gibbs or Helmholtz energy. And of course, lastly, we have said that we can use the Gibbs-Helmholtz relationship in finding the work or the work function or the maximum work which can be performed by a system. So in this specific case, we see that we have a wide range of this particular application for the Gibbs-Helmholtz relationship. And of course, they're going to be applicable and of great significance for us as we go ahead. Now, in this particular case, we're going to use the concept of course, the Gibbs-Helmholtz equation. And this is going to be giving us of course, a way of finding the partition function in terms of this particular Gibbs-Helmholtz equation. Now, in this case, I'm going to give this specific relationship. Of course, we have done a derivation of this Gibbs-Helmholtz equation in our previous videos, and I'm going to put a link of those specific videos in the description box of this particular video. Kindly check and, of course, give us a feedback in the comment section. So we're going to have this one given in this specific description, and this is going to be described under constant, of course, pressure given as such. So this is going to be the relationship between the Gibbs and Helmholtz free energy, and it's going to be referred to as the Gibbs-Helmholtz equation. Now, in this case, we can represent. So in this case, we are going to see that this basically represents the Gibbs energy at constant pressure. And we can have an analogous version of this specific representation by considering the Helmholtz free energy. And of course, this is going to give us a way of representing the internal energy of this specific system. Now, an analogous equation to this specific equation for the Helmholtz free energy can be given in terms of the partial derivative with respect to temperature over A all over T. And this is going to be under the condition of a constant volume given as such, and this is going to give us the aspect of internal energy and of course the inverse of the square of this temperature given as such. So this is an analogous equation of this particular form, and of course from this we can find a substitution for this element of internal energy, and of course find the relationship or an appropriate representation of the Gibbs-Helmholtz relationship in terms of a partition function. Now, from our previous discussion, I had given this specific aspect of internal energy, and I've said that internal energy in terms of a partition function can be given as a Boltzmann's constant, the product of Boltzmann's constant and the square of temperature, and the partial derivative of the natural logarithm of Q, of course, with respect to temperature given as such. And we have said that this basically is going to be taking place under the condition of a constant volume. Now, this basic equation is going to assist us try to represent this specific Helmholtz energy in terms of the partition function, and that is going to be achieved through a substitution of this particular numerator using this equation. So therefore, I'm going to have this version of the equation represented in terms of the partial. Just to use this space. So I'm going to have the partial derivative with respect to temperature over this Helmholtz energy over T, and this is going to be under constant volume is given as, so a substitution for this is going to give me this negative K B the square of T, and then I'm going to have the natural logarithm of Q with respect to temperature under constant volume given as such. And of course, this is going to be given with a multiple of times 1 over T, which basically I can just divide as the square of T. So we can do a simplification of this one by cancelling out the, of course, the same factors, whereby we have the square of T cancelled out, as such. And of course, we're going to do a subsequent rearrangement or a simplification by, of course, using integration. And of course, it's going to assist us, of course, by integrating both sides of this specific equation. That is going to assist us, of course, find a representation of the Helmholtz energy in terms of a partition function. So basically, an integral on this specific side of the equation, or rather, let me just simplify it. I'm going to have this one as a partial derivative of this a over t, and then this is under constant volume is equivalent to negative k b the partial derivative of q with respect to temperature, constant volume. And of course, I'm going to have a simplified, I'm going to have an integration of this. Now, we have discussed various laws of integration in our previous discussion, and I'm going to consider both sides and integration with respect to temperature. And of course, this is going to give me a minus a. Now, I'm going to give this one because of space. Presume that the various laws that we have discussed on various derivatives of natural logarithms and exponents are going to be applicable in this. I'm also going to put a link of that specific video in the description box. So therefore, this is going to reduce in a form of this specific representation, whereby we are going to have the change in Gibbs energy from this specific, of course, initial state of 0. This is at absolute 0. We're going to have a naught given as, of course, an integration of a constant of integration. And then we're going to have the negative kbt natural log over q given in that specific case. So this is going to form our representation for the partition function of the Gibbs-Helmholtz relationship. And in some cases, of course, we're going to have it applicable just as other equation which represents the partition function of various thermodynamic variables. So catch us in our next videos. We're going to look at various other forms of thermodynamic variables. But of course, we are going to also be including the different, of course, sets of perhaps problem sets done in terms of videos, which are going to assist us have a clearer picture of the applications of these particular functions in various thermodynamic variables. So that is it for now, guys. Bye, God bless you. Catch us in our next video.